Hello, AP Physics students. We have another problem for you today. We're going to do problem 26 from chapter number 6. And topics we're going to talk about today, springs and conservative, non-conservative forces and potential energy. So lots of good stuff in this video. So this problem states that I have a spring with a spring stiffness constant K of 440 newtons per meter, and that this spring, how far must this string be stretched so that it stores a potential energy of 25 joules. All right, lots to talk about today, physicists. Lots to talk about. Lots of really good stuff. So let's talk about springs. All right, here I have a spring. All right, springs are governed by what we call Hooke's law. All right, and you don't have to know the name of Hooke, but Robert Hooke, arch enemy of Isaac Newton. Long story. Anyway, here's an equation for springs. The force exerted by a spring is equal to minus kx, where k is the spring constant, and that is measured in newtons per meter. Okay, so for instance, to stretch this spring 1 meter, I would have to pull with a force of 440 newtons. To stretch the spring 2 meters, I would have to pull with a force of 880 newtons, etc., etc. All right, so that's what we mean by a force constant. Okay, how stiff is the spring? A big K means a really stiff spring. A little k means not a stiff spring. Now, if you're dealing with a car, you probably want a stiff spring. If you're dealing with a pen, you probably want not a stiff spring. Okay? So anyway, that is Hooke's law. Why the negative sign, people say sometimes. Why the negative sign? Okay, so if this is my spring, right? Okay, if I move it this way, right? So if I displace the spring x this direction, what way does the spring pull? It pulls back this direction. So the displacement is in the opposite direction the force is exerting. Likewise, if you have like a spring like on your mattress or on a car, when you compress those springs, they push back the other way. So that's springs, all right? So twice as much force to stretch a spring twice as far. Okay, so back to here. So let's talk about forces. There's two types of forces we come across. Conservative forces and non-conservative forces, okay? A conservative force is a force like gravity or springs, where if you do work against the force, the energy gets stored, okay? So when I stretch this spring, that energy is stored in there, okay? That's a conservative force, all right? Now, a non-conservative force is one like friction, okay? So when I do work against friction, say by pushing on an object, right? I did work, but I can't get that energy back, right? In the term, now the energy didn't disappear, I just can't get it back in a useful form, okay? So when dealing with a conservative force, you can define what's called a potential energy function. And what that means is the potential energy or stored energy that you have, energy, is equal to the work done against the conservative force. So for instance, if I want to figure out how much energy I have stored in this spring right now, I calculate the amount of work I've done against that conservative force, okay? So in this problem, we want to calculate the amount of potential energy we have, right? So to calculate the potential energy, we're going to have to calculate the work we've done on the spring, okay? So how much work would we have to do? Well, we'd have to do 25 joules worth of work to get 25 joules worth of stored energy. Okay, well, work is force times distance, right? But I got a problem here. My force is constantly changing with this spring, right? The force is 440 newtons here, 880 newtons there, right? I'm exaggerating. I didn't stretch it a meter, but you get the idea here. So what I'm going to have to do is make a little graph here of force versus distance, all right? And the graph is going to look like this, okay? Why is it going to look like this? Well, when the spring is displaced 0 meters, there's 0 force. And the more distance I displace the spring, the more force I get, okay? So if I call this distance x, all right, when I pulled the spring a distance x, all right, the force will be kx, okay? So kx by Hooke's law, all right? Now to find the work here, I need to find the area underneath this curve. So the work done in stretching a spring from here to here is equal to the area underneath the force versus distance curve. Well, I don't even need calculus to do this. This is a triangle, right? So the area of this triangle is 1/2 the base times the height, right? Or 1/2 x times kx, right? So the work that I've done in stretching a spring from the equilibrium position to a distance x is equal to 1/2 k x squared, all right? And that's an equation that's actually on your equation sheet, I believe. So work done to stretch a spring, all right? And that is going to end up equaling our potential energy. So lots of background information here, but let's solve our problem here finally once and for all. Okay, so the potential energy is equal to the work is equal to 1/2 k x squared, right? And we want to know in this problem how far, right, have we stretched the spring, right? What is this distance x? We have to stretch the spring to get 25 joules worth of stored work. Okay, well, let's do a little algebra here. 2 times w divided by k is equal to x squared. Do the square root of both sides, and I get x is equal to the square root of 2 times 25 divided by 400, right? And if I type that into my calculator, I believe I get, what is that, the square root of 1/8, which is about 0.36 meters, okay? So I'd have to stretch the spring 0.36 meters to store 25, to do 25 joules worth of work against the spring, which translates into a potential energy stored of 25 joules. All right, nice work, AP Physics students. For your funny cartoon today here, we have one for you, and here it is. A little slower next time, Terry. He does not understand centrifugal force. All right, nice work, AP Physics students.